Hi, this is Mrs. Allison, and this is a tutorial that will follow the notes 3.1a a little bit quicker. We're going to talk about U-substitution today, or the substitution method. So we call it U-substitution because often what we use is the variable u for the substitution, although it does not have to be u. If you just Google substitution method, you will get a plethora of videos, and most of the time the variable used is u. So U-substitution is simply a technique. It is just a way or a method that we can use to be able to help us integrate. Sometimes integration can be done just by inspection, meaning we can look at it and say, okay, I know how to undo those steps. And sometimes we need a little bit of help. Sometimes it's a little bit harder to see how to work our way backwards, how to pedal our way backwards. And so we need some help. And the idea of U-substitution is just that. When we use U-substitution, or how we know we can use U-substitution, is if we would need a chain rule when doing derivatives. So what is the chain rule for derivatives is what is comparable to that is U-substitution. So U-substitution just says integration by substitution evaluates integrals if we let u equal some function g of x and it's differentiable. And then we have some integral of f of g of x times the derivative of g of x. And what you can see is this looks like the chain rule. So basically, U-substitution unchains the chain rule. And the steps that we go through, while I can give you the steps, really are better explained once we look at some problems. What we're going to do is we're going to pick a u value that represents some function. Oftentimes the u that we choose is going to be what would be the chain, or like the more complicated part. So if we were taking derivatives of something and we needed to use the chain rule, what is it that we would have to chain? That will be the u value that we choose, or the higher powers if we have them. Then what we're going to do is we are going to take the derivative. We're going to derive that u equals g of x. Now, it does look like this. Du over dx equals g prime of x. But what we're going to do is we're going to separate it, write it in more of a differential form. So du equals g prime of x dx. And then we're going to make some substitutions into the original function to convert the entire integral in terms of that variable that we've chosen. So in our case, u. Then we're going to integrate with respect to that new variable u. And then in the end, since we're doing indefinite integrals, we are going to replace that value back with g of x. So let's look at a couple of examples. One of these examples we definitely could do without U-substitution. And one of these examples is really better done with U-substitution, and I'll let you kind of think through how you might choose to do these. So let's look at this first example. In this first example, I really don't have necessarily a chain rule, but I do have a more complicated function. I have this function t cubed plus t squared. And so what I'm going to do is I'm going to let u equal t cubed plus t squared. And then what I'm going to do is I'm going to take the derivative of this. And when I take the derivative of this, normally we would get du over dt equals 3t squared plus 2t, but I'm going to write it in this differential form where this dt is on the other side. So I have du equals 3t squared plus 2t dt. Now, what I hope you notice is that this expression right here, this 3t squared plus 2t dt, is actually already in this problem. Now, it's not written exactly in that order, but that's okay because multiplication's commutative. So I could rearrange this just a little bit. Now watch what's going to happen. I'm going to rewrite my integral. Oops, I want a black pen. I'm going to rewrite my integral. And we know that we let t cubed plus t squared be u. So I've got the integral of u. And I know that 3t squared plus 2t dt is equivalent to du, this piece right here. So really what I'm doing is I'm taking the integral of u du. Well, that's pretty easy to integrate. I can use the power rule here, which would give me u squared over 2 plus c. So I've just gone through the steps. So let's review the steps. Set u equal to g of x. We did that. This was my function that I chose, a more complicated function. I took the derivative with respect to t, or whatever variable's in there. In my case, it's t. This example was x. I'm going to substitute all of those values, u and du, to convert the original integral into an integral with just the variable u. Then I computed the integral within the new variable u. And now what I'm going to do is I'm going to go back to this integral, and in place of the u, I'm going to put back in what I let u be, which was t cubed plus t squared. So I've got t cubed plus t squared over 2 plus c. And this, let me just rewrite this just a little bit prettier, is the antiderivative. I don't want that all over 2. We'll just do that. This is the antiderivative of that original problem. Now, are there ways we could have done that without using U-substitution? Sure. If you recognize that those are derivatives of one another, or that 3t squared plus 2t is the derivative of the t cubed plus t squared, it might be easy for you to think about. But if you don't recognize that, this is a place where U-substitution comes in. Now let me show you a problem that would be a little bit more challenging to think about in terms of use without U-substitution. So let's look at this next one. We've got the antiderivative of 6x squared over the square root of 4x cubed minus 5 dx. Now remember that dx is just notation. It's required to be part of that integral, so we need that there. But let's look at this problem. If I didn't have this integral here, and I were to take the derivative of this, what part of this would give me a chain? Hopefully what you notice is that the part that would give me the chain is this 4x cubed minus 5. Well, since that's the part that would give me my chain, I am going to let u equal just the 4x cubed minus 5. The square root is not part of the chain. It's because there's a function inside the square root that we have a chain. And now I'm going to take the derivative of this using that differential form. So du equals 12x squared plus 0 dx. Okay, now like the last one, I'm going to look and I'm going to say, okay, where is this represented in my integral, my original integral? Well, I see the dx part. I even see the x squared part, but the problem is it's not quite right? This is a little bit off. So what I'm going to do now is I'm going to take and multiply this entire expression, this du, by 1/2. So we would get 1/2 du equals, well, half of 12 is 6x squared dx. So now I have manipulated this to make it so that I have the exact expression 6x squared in terms of the 6x squared dx. So really what this looks like, if I rewrite this, this would be the integral of, well, if I replace the blue parts, that 1/2 du, I would have 1/2 du divided by the square root of u. Now that maybe doesn't look that much neater right now, or that much easier. But remember, we have the scalar rule that says I can pull a 1/2 out. So I would have 1/2 the integral of, and typically we don't write that differential du up in the numerator. So we might just say this, 1 over the square root of u du. These are equivalent expressions. And in my mind, this is a much easier integral to solve than is the original, because I can undo this integral. And it may even help you to rewrite it one step further by saying 1/2 the integral of u to the negative 1/2 du. And now what we'll do is we will go up a degree, we'll divide by that degree, but I can't forget the scalar that was already out front, plus c. And when I substitute everything back in, not sure how that got detached. When I substitute everything back in, or simplify this, really all I get is the square root of u plus c. And now going back in with the u that I let u be, we would have 4x cubed minus 5, the square root of all of that, plus c. So the idea of U-substitution is, again, it's just a technique. You might find it's easier to not use U-substitution. And there's a couple examples on the back where that might be the case. But you might find it easier to use U-substitution as a way to anti-differentiate. So let's look at a couple other examples. All right, here's a couple of other examples. Let's start with this first one that says the sine of 4x dx. I'm guessing that you might be able to do this without U-substitution. So let's look at it with U-substitution, and then you can make the decision as to whether or not you think U-substitution helps in this case. Again, it's just a technique. If I were to look at this as if it were just a derivative, so I didn't have that antiderivative, and I wanted to anti-differentiate, if I wanted to take the derivative, my chain would be the 4x. So, keeping that in mind, I'm going to let my u be 4x. And if I take the derivative of this, I would get du equals 4 dx. And I can't have that because that's not what's in my problem. I don't have a 4 dx, I just have a dx. So if I multiply everything by 1/4, I would get 1/4 du equals dx. Now the substitution becomes very clean. I'm going to replace dx with 1/4 du. And so then this integral becomes the integral of the sine of u, and then this would be 1/4 du. Now that notation looks a little funky, so I'm going to go ahead and rewrite that. 1/4 times the integral of the sine of u du. Now, looking at these two, yes, this is a very clean U-substitution. It works nicely. But is this expression really that much simpler than this one? I don't know. I'm going to let you be the judge of that. I don't think it necessarily is. So if you see this antiderivative done differently, great, do it differently. So once I take this, the antiderivative of the sine would be negative cosine. So this would be negative 1/4 cosine u plus c. And when I make my substitution back in, we would have negative 1/4 cosine of 4x plus c. Again, you certainly could work your way backwards. All right, if you're feeling adventurous, hit pause and try the next one. Hopefully you had a chance to look at this one, and hopefully your first thought was, okay, if I were doing the derivative of this expression, y cubed plus 1 squared, I know that the chain would come from this y cubed plus 1. So I'm going to let u equal y cubed plus 1. And hopefully then you went and took the derivative, and we'd get 3y squared dy. Do you see any problems? Okay, there is a big problem. And the big problem is I don't have this expression anywhere in my integral. I have a dy, but there's no way I can move anything to the other side. Let's say, for example, that I did, and I'm going to erase this in just a second. I would have 1 over 3y squared du equals dy. But do you see how that would defeat the purpose? Remember, the steps say we need to get the whole integral in terms of one variable. So our goal is to get it in terms of u. Well, if I still have a 3y squared expression, then my integral is not in terms of u. And so there are times when using U-substitution doesn't in fact work. Okay, so we cannot use U-substitution here. I'm just going to abbreviate it U-sub because there is no expression. There's no, that was meant to be a du. There's no du, dy expression in there. It's not there. So we're not going to use U-substitution. But does that mean we can't take the antiderivative? Of course not. So sometimes we need to use algebra, basic algebra. So I'm going to rewrite this by expanding the squared. And if I expand the squared, this will give me y to the 6th plus 2y cubed plus 1 dy. This becomes a pretty easy polynomial to take the antiderivative of. So I'm going to go up a degree, divide by that degree. Go up a degree, divide by that degree. Go up a degree, add the plus c, and then simplify as much as I can. So we'd get y to the 7th over 7 plus y to the 4th over 2 plus y plus c. All right, go ahead and pause. Go ahead and hit pause and try the next two and see what you can come up with. And I don't put any more tricks. There's no more tricks on here. All right, hopefully you had a chance to try these. If I were to use U-substitution on this one, I would let u be theta squared. And then I'm going to take the derivative of this. So we'd get du equals 2 theta d theta. The problem is I don't have a 2 theta d theta. I have a 3 theta d theta. So I need to rewrite mine in terms of 3 theta d theta. So I'm going to go ahead and multiply this entire expression by 3/2. So we say 3/2 du equals, well, if I multiply that, I would get 3 theta d theta. Now I haven't changed the problem any because I multiplied an entire equation. And now I can rewrite my integral. This will become the integral of the cosine of u times, this is kind of funny notation, 3/2 du. And once again, I tend to pull my scalar out. So 3/2 times the integral of the cosine of u du is what this would look like. So if I anti-differentiate this, 3/2 stays. This would be the sine of u plus c. And substituting back in u, we would get theta squared. Now, could you have come up with that without using U-substitution? Probably can. So if you didn't get that one and you want to try the next one, go ahead and hit pause. Otherwise, let's keep going. In this problem, what I would choose to be u would be the part that would be a chain if I took a derivative. And the inside function here is sine of x. So I'm going to let u be sine of x. So du would be the cosine of x dx. And this one, finally, I have a nice, easy substitution. I have a cosine of x dx. So if I rewrite this integral, this would be the integral of u, because that's what sine was, or yeah, u was sine, u squared du. U squared du. So I'm going to go up a degree to anti-differentiate. So I would have u cubed over 3 plus c. And substituting back in for the u would give me sine cubed x over 3 plus c. So again, U-substitution is just a technique. Sometimes it comes in very handy, and sometimes it's easier to reverse engineer the antiderivative. Sometimes we can look at it and see that pattern and say, okay, what got me to here? How do I work backwards? And that's okay. So hopefully this helps just a little bit. We will continue the idea of U-Substitution and a little bit later. And have a good day.